Hello friends. Now today we are going to start with the new unit, unit number 4, where we are going to study curve tracing. Now in this lecture we are going to see some basic concept of curve tracing and we are going to see some rules to trace the Cartesian curve. Okay. So let us start with some basic concept that we are going to need while tracing the curve. The very first point is multiple point. Now, a point through which more than one branches of curve is passed is called as a multiple point. That means if we are having a single point and the many branches of the curve is passing through it, then that point is called as multiple point. Okay. Then the double point is what? A point through which two branches of the curve is passed is called as a double point. Okay. Now there are basically two different kind of double points we are going to see. One is node and one is cusp. Okay. So what is node? A double point is called as a node if distinct branches have the distinct tangent. So we are going to see the what is node in the next slide. Actually, what is node and what is cusp. So cusp is what? A double point is called as a cusp if distinct branches have the common tangent. So if we are having a distinct tangent, then it is a node, and if we are having a common tangent, then it is a cusp. Okay. So in the diagram you will get it. What is node and what is cusp? I'll explain it. Then what is the point of inflection? A curve has an inflection at point P if it changes from concavity upward to concavity downward or vice versa. Again, we are going to see the diagram of this. Now the asymptote is a very important concept. So asymptote is what? It is a tangent to the curve at infinity. Okay, that means at infinity that tangent is very close to curve, but it never touches the curve. Okay, that is called as a asymptote. Tangent is the asymptote is nothing but what? It is a tangent to the curve at the infinity. Okay, so as I told you, these are the diagrams of node, cusp, point of inflection, and the asymptote. So as I told you, node is nothing but what? We are having a two different branches, and we are having a point which is a double point, and for two distinct branches we are going to have a two distinct tangent. So if you look at this two branches, this branch and this branch, so if you draw the tangent to it, so this is one tangent, this is one tangent, actually it should touch it. So that since the two distinct branches we are having a two distinct tangent, then that's why it is called as a node. But if you look at the second part, if you look at this diagram, here we are having two different branches. This is one branch, this is another branch, but for both the branches we are having a single tangent, and that's why it is called as a cusp. Okay, so I hope you are getting the difference between the node and the cusp. So for a node, for two distinct branches we are having a distinct tangent, and for a cusp, for a distinct branches we are having a common tangent, then it is called as a cusp. Okay. Now what is the point of inflection? So as I told you, this is the point of inflection point. So here we are changing the concavity downward and concavity outward. That's why it is called as a point of inflection. And the last point is asymptote. So if you, this line is called as the asymptote of this curve because this curve will be very close to that line, but it will never touch to that line, so that it is called as a asymptote. So asymptote is nothing but what? It is a tangent to the curve at infinity. So basically in this unit we are going to study three different kinds of curve. The very first curve is Cartesian curve. Okay. So in a Cartesian curve we are going to have an equation like f of xy is equal to c. So we are having an equation in terms of xy. Okay. Then in a polar form we are going to have an equation in terms of r and theta, where c is a constant. Okay, and in a parametric form, it is not printed over here, we are going to have x is in terms of t and y also is in terms of t. So we are having a different parameter over here on which x and y are dependent. So I repeat, here in a parametric form, x will be a function of some t and y is also a function of t. Okay, so t is a parameter over here. So these are the three kinds of curve that we are going to study over here. So we are going to start with, first of all, the rules for tracing the Cartesian curve. So one by one we are going to see how to trace the Cartesian curve. Then we are going to see how to trace the parametric curve, and then we are going to see how to trace the polar curve. So while tracing the Cartesian curve, there are 6 different points that you have to take care of. So very first point over here is symmetry. So very first we are going to check out the symmetry of the curve. Then we are going to check out whether the origin is passing through the curve or not. And if the curve is passing through the origin, then we are going to find out tangent at origin also. Okay. Then the third point we are going to see is intercept. So basically 2 kinds of intercept we are going to see, x-intercept and y-intercept. Now x and y-intercept is nothing but what? We are going to check out the point of intersection on x-axis and the y-axis. And then as I told you, asymptote is nothing but a tangent to the curve at infinity that we are going to see here. So we are going to check out 2 kinds of asymptote, parallel to x-axis and parallel to y-axis. Then the next is region of absence. So we are going to find out an area or a region in the graph where the curve will not be present. That means that is called as a region of absence. Okay. And the last and a very important point is the spatial points on the curve. So what are the spatial points? So basically the intercept that you are going to get, that is x intercept and y intercept, that will be treated as a spatial points. Okay. So the 6 points we are going to see now in details. So how to check the symmetry of the curve? So symmetry, there are again some subtopic in the symmetry. The very first thing we are going to see the symmetry about x-axis. So symmetry about x-axis, how we are going to check out? If the power of y is even, every power of y is even, then we are going to have a symmetry about x-axis. Or we can say after replacing y by minus y, if the equation remains unchanged, then the curve will be symmetric about x-axis. Okay. Or here it is not actually visible, but if every power of y is even, then we are going to say that the curve will be symmetric about x-axis. Similarly, symmetry about y-axis, when we are going to have symmetry about y-axis, if we replace x by minus x and equation will remain unchanged, then we are going to have a symmetry about y-axis. Or we can say if all powers of x in the function are even, then the curve is symmetric about x-axis. Okay. So what you have to remember, symmetry about x-axis, power of y should be even. For symmetry about x-axis, power of y should be even, and for symmetry about y-axis, power of x should be even. Okay. Now the next thing is symmetry about origin or in opposite quadrant. So for a symmetry about origin, if you replace x by minus x and y by minus y, this is the thing that you have to remember. If you replace x by minus x and y by minus y, and if the equation remains unchanged, then the curve is symmetric about origin, or we can say it is symmetric in the opposite quadrant. Okay. Then the symmetry about the line x equal to y. So again, since we are checking for x equal to y, what you have to do, replace x by y and y by x, and if the equation remains unchanged, then we are going to say that the curve will be symmetric about x equal to y line. Here if you want to check out whether the curve is symmetric about x equal to minus y, what we have to do is we are going to check out, we are going to replace x by minus x, x by minus y, and y by minus x, and if the equation remains unchanged, then we are going to call that the curve is symmetric about x equal to minus y. Okay. So here if you look at this curve, here we are having the power of y is even, therefore the symmetry is about y-axis. Here if you look at this thing, x equal to y, because in this equation if you replace x by y and y by x, the equation remains unchanged, so this curve is symmetric about x equal to y line. This curve is symmetric about both x and y axis because the power of x and y both are even, that's why it is symmetric about x as well as y. Okay. Then here symmetry in opposite quadrant, because if you replace x by minus x and y by minus y, the equation will x by minus x and y by minus y, you are going to get the same thing. So you are going to have, this is symmetric about origin or in the opposite quadrant. Okay. So this is about the symmetry. So in a symmetry, what you have to check out? Symmetry about x-axis, symmetry about y-axis, symmetry about x equal to y line, symmetry about x equal to minus y line, symmetry about both the axes. Okay. So let us go to the next point. Next point is intercept. That is point of intersection on x and y axis we are going to find out. So how to find out the intersection on x axis? So simply on x axis we know y coordinate is always 0. So if we put y is equal to 0 in a given equation of the curve, and we'll get a corresponding value of x, and that is nothing but the intersection with the x-axis. Similarly, if you want to find out y-intercept, what you are going to do, you are going to put x is equal to 0 and find out the corresponding y-intersection point. When we are going to say that curve is passing through the origin, whenever the point 0, 0 will satisfy the equation of the curve, then we are going to say that the curve is passing through the origin. Okay. So here you can check out, when you put x and y is equal to 0, this curve will satisfy it, so that it is passing through origin. Here, even over here, when you put x and y is equal to 0, it will satisfy it. Here also, here we have, if we put x and y equal to 0, it is not going to satisfy the equation. That's why the curve is not passing through origin. Here also, if you put x, y is equal to 0, you are going to have c square. 0 is equal to c square, so it is not passing through origin. Okay. Now the next thing is tangent at the origin. As I told you, we are going to check out origin as well as tangent at the origin, if it is passed. If curve pass through the origin, then tangent at origin can be obtained by equating. This is the important thing. So whenever you want to find out the tangent at origin, what you have to do is you have to equate the lowest term of the equation to 0. Okay, that means what you are going to do, whatever the terms you are having with the lowest degree, you are going to take it on one side, and then we are going to equal it to 0. If, for example, if you look at this, so we are having y square is one term and 4ax is another term. But the degree of y square is 2 and the degree of 4ax is 1. So we are going to equate 4ax to 0. Okay, and we are going to get the tangent at the origin. Then the next point is asymptote. So asymptote, as you know, is asymptote is nothing but a tangent to the curve at infinity. And basically we are going to see two kinds of asymptotes: asymptote parallel to x-axis and asymptote parallel to y-axis. So this is a very important part, how to find out asymptote parallel to x-axis. We are going to equate the coefficient of the highest degree of x to 0. This is very important thing. So if you want to find out the asymptote parallel to x-axis, what you have to do is you have to equate the coefficient of highest degree of x to 0. Okay. Now suppose the coefficient of highest degree of x is y is equal to a, then the asymptote is parallel to x-axis. Okay. If the coefficient of highest degree is constant, the constant you cannot equate it to 0. That means you are not going to have a asymptote parallel to x-axis in that case. Similarly, if you want to find out asymptote parallel to y-axis, what we are going to do, we are going to equate the coefficient of highest degree of y to 0. Okay. Now again the same kind of argument we can do. If the coefficient of highest degree of y is x equal to a, then it is asymptote parallel to y-axis. Obviously x equal to a line will be parallel to y-axis. And if the coefficient of highest degree of y is constant, so we cannot equate constant to 0, so that in that case we are not going to have a asymptote parallel to y-axis. Okay. Oh, sorry. So this is about the asymptote part. Now let's move to the next part. So see, here I have drawn some asymptotes. You can see over here. So this line is the asymptote which is parallel to y-axis. Okay. And see, if you look at this line, this is very close to this two curve, but they are not touching it. Okay. Similarly, here if you look at this line, is the asymptote, because it is parallel to this curve on both the side but not touching it. So that is also asymptote. Okay. Now one more kind of asymptote is there. Actually in our syllabus we are not going to study this. Very rarely there will be a chance of asking a question on oblique asymptote. Okay, so let's skip this. Then the next is region of absence, or we can say it is region of existence. Okay, sometimes it depends what they will ask you, but we are going to check out the region of absence over here. To find out the region of absence, what we are going to do, so first of all we are going to express the equation in terms of y equal to f of x, and then we are going to find out the values of x, such a values of x which will give you y square is equal to y square is less than 0. So for whatever values of x, if you are getting y square is less than 0, that is negative, that y square is negative means what, your y will be imaginary. Okay, so if you are getting y is imaginary for some particular interval of x, then that interval is called as region of absence. Okay, so in short, if possible, we write on y code f(x) and find values of x for which y square is negative. If for this interval a to b, then the curve does not exist for this region. Okay, and we can say on the other hand, if y square is positive, then in that particular region it will exist. Okay, fine. Similarly, for x, if you are having for some y x square is negative, then in that region the curve will not present. Okay, and this is the last point with the help of which we'll get a better idea about the curve. So these are something that you are supposed to remember. So for any point, basically these are the points which are nothing but the intercept. Okay, remember this. So we are going to check out this special point for intercept. Okay, so at the intercept we are going to find out the derivative dy by dx at the point P, and if that derivative value is equal to 0, then we are going to say that at that point P we are going to have a tangent parallel to x-axis. Do remember this. If the dy by dx value is equal to infinity, then at the point P we are going to have a tangent parallel to y-axis. Okay, if dy by dx is greater than 0, then in fact we are not going to have this kind of thing. Either we are going to have a 0 or infinity, or you may have a 0 by 0. Remember, whenever you are going to have a dy by dx is equal to 0 by 0, then in that case we are going to have a cusp. Okay, so do remember this thing. These three things are important. Okay, so that's it for today's lecture. In the next lecture we are going to see the examples on Cartesian curve.